So in the previous lectures we discussed calculation of the deflection and slope of a cantilever beam subjected to a point load at free end and uniformly distributed load over entire span. Now let us consider the same cantilever beam subjected to a load varying linearly from 0 at free end to W Newton per meter length at fixed end. Based on given data, so we formulate the problem. This is a cantilever beam. One of its end is fixed, labeled as A. Other end is free, that is B. So what the problem? 0 at free end, this is 0, and W Newton at fixed end. So linearly varying load. Graphically, so the loading system is represented as shown in figure. This is the one. The entire length of the beam is as usually taken as L. Here there are two difficulties. One is calculation of the total load for a particular portion, at which point it is concentrated while formulating the bending moment equation. This is only the new thing. So as we know that the governing differential equation for the deflection EI into d square y by dx square is equal to mx. Say equation number 1 for example. Here we have to calculate the mx. For calculating the mx, let us consider section xx at a distance small x from the free end as usually. Here I would like to take the origin at B, so it means the x 0 at B and x is equal to L at A. It means the x value begins with 0 from B towards left. So here while calculating the shear bending moment at a section xx with uniformly distributed load for a portion say as CV, I would like to redraw a particular portion between the section xx and B for our convenience. That is, this is the entire beam, need not worry about. This is the W load. So this is entire beam. So the overall height of the beam is W. This is L. This is L. The rate of loading is, as we know, that this is 1. So this is the B. This is A. In which let us consider a portion this is a portion triangle CBD with a distance or base x. So take out that portion only. This is the triangle CD. This is the section XX. This is the B. Here the base of this one is as x. The rate of loading is distributed as shown in figure. Keep in mind the intensity of load at section XX is taken as W suffix x. It means initially we have to calculate the intensity of load. Calculation of intensity of load intensity of load at section XX. That is the important point. If you observe the geometry, so this is capital W, this is the W suffix X, this is the L, this is X. From the geometry and from the similar triangles, W suffix X by capital W is equal to small x divided by L. So from this equation, W suffix X is equal to Wx divided by L. So this is say as important one. So now calculate the total load. What about the total load? The total load is taken as area under this triangle. So BCD. What about that one? The total load of a right angle triangle of base X with height Wx, that is half into so base is X and the height is W suffix X. This can be rewritten as, that is half into small x into what about the Wx, that is capital W into X divided by L. Finally that becomes, so Wx square by 2L. This is the total load. So at which point it is concentrated, that is the second point. So it is always at the centroid of the triangle BCD. So this is the total load, that is Wx square by 2L. While taking moment of a force with respect to the section XX, you must measure the perpendicular distance from the section X only. It means this is the perpendicular distance from the section XX. It is always 1/3 of X, since it is measured from the vertical side, vertex, that is 1/3 of X. It means that is the location. That is the location, that is equal to 1/3 of X. So what about the moment produced by the Wx square by 2L about section XX, that is Wx square by 2L into half into X. So that is the bending moment equation at any section. Therefore, Mx is equal to, so Mx is equal to Wx square by 2L into 1/3 of X. So that is the bending moment equation. So now we know that therefore Mx is equal to, what about that equation? So Wx square by 2L, Wx square by 2L into 1/3 into X, that is equal to Wx cube by 6L. Substitute this value in the governing equation as Ei into d square y by dx square is equal to. Next, let us see the convention, that is sign convention. So you must take the sign convention as a negative because it produces the hogging moment. So it is minus, right? This is minus of Wx cube by 6L, say equation number 2. Suppose if you want to formulate the slope and bending moment equation it is integrated 2 times. Say for equation for slope. Equation for slope. What about the equation for slope? That is obtained by integrating the equation number 2. So, equation for slope is obtained by integrating the equation number 2 once. That is equal integral ei into d square y by dx square is equal integral minus wx cube by 6l. After performing the integration, that is ei into dy by dx is equal to minus. So w by 6l is constant. So x power 4 by 4. As we know that integral x power n into dx is equal integral x power n plus 1 by n plus 1. And there is a constant or a constant of integration. Say equation number A. So in equation number A, we have to find out the C1 value. So the C1 value is obtained by imposing the boundary conditions. I think that so dy by dx is equal to 0 yet x is equal to L. As we know that in the earlier classes we discussed about the slope and deflection at fixed end. The slope and deflection both are 0 at fixed end. So since it is 0 at fixed end, so as per the taken problem or consideration, so dy by dx is equal to 0 at x is equal to L. At x is equal to L. Simply substitute x is equal to L in equation number A. So ei into, what about the dy by dx value? That becomes 0. That is 0 is equal to minus w by 6l into x power, x is replaced by l, that is equal, x is equal to l, that is equal, it is, what about that is equal, so L power 4 divided by 4 plus C1. So therefore C1 becomes, this is once, that is equal, C1 is equal to WL cube by 24. Substitute C1 value in equation number A. So therefore equation for slope is ei into dy by dx is equal to minus wx by 24l plus wl cube by, so this is x power 4, sorry, that is wx power 4 by 24l, then wl cube by 24. Then you can find out the slope at any point, say as at x is equal to 0 and at x is equal to L. So you can find out the slope at x is equal to 0, that becomes simply WL cube by 24. At x is equal to L, we will get the 0. So it means slope at B, that is at x is equal to 0. If you substitute this value ei into dy by dx is equal at x is equal to 0, this term becomes 0 by 24L plus WL by 24. So therefore dy by dx is equal so the WL 1 by EI into WL by 24. This is the slope at B. Then you can find out the slope at A also. So whenever substitute x is equal to L in this equation, EI into dy by dx is equal, this becomes minus WL by 24 plus it becomes WL by 24. These two values are cancelled out to simply dy by dx is equal to 0 at A. So now let us calculate the equation for the deflection. Now equation for deflection. Equation for deflection. What we have to do? Simply integrate the equation number 3 once again. Equation number 3 once again. This is the equation for the slope. So what about that value? Let us rewrite that value. EI into dy by dx is equal to minus wx power 4 by 24 L. So that is equal to EI into dy by dx minus w. So x power 4 by 24 L plus WL cube by 24. WL cube by 24. This is the equation number 3. If you integrate this equation once again, you will get the deflection by integral EI into dy by dx is equal integral of minus wx power 4 by 24 into L plus w L cube by 24. So after performing the integration, the above equation becomes EI into y is equal to minus w by 24 into L x power 5 divided by 5 plus WL cube by 24 into x plus C2. The constant of integration to C2 is obtained by enforcing the boundary condition. As we know that deflection y is equal to 0 at x is equal to L. So simply substitute it. EI into 0 is equal to minus W by 24 L into L power 5 by 5 plus WL cube by 24 into L plus C2. Here this is 4 times, so it becomes L power 4. So simply 0 is equal to minus W into L power 4 divided by 24 into 5 plus WL power 4 by 24 plus C2. This can be rewritten as our convenience, that is WL power 4 by 24 is taken as common, minus 1 by 5 plus 1 plus C2. So that is equal to WL power 4 by 24. What about that? 5 minus 1 plus 5 plus C2. So this is the simple way to calculate that. That is equal to WL power 4 by 24 into, what about this value? Very simple, 4 by 5 plus C2. So that is equal to WL power 4 by, so 4 6 times. That is equal to 30 plus C2. Therefore, C2 is equal to WL power 4 by 30. WL power 4 by 30. Substitute this value in this equation, say as equation B. Equation B. Finally, that becomes, so what about that value? EI into EI into Y, that is equal to EI into Y EI into Y is equal to minus W x power 5y minus, this is minus W into x power 5y, so 120L, right? This is, whatever that equation, this is 120L plus WL cube into x plus WL cube into x divided by 24 plus, what about the C2? The C2 value is WL for 4 by 30 plus WL power 4 by 30. So now you can calculate the slope at x is equal to 0. Deflection at x is equal to 0. So therefore, deflection at x is equal to 0. So at x is equal to 0, EI into y is equal to minus W into 0 power 5 by 120 into L plus WL cube into 0 by 24 plus WL power 4 by 30. I think that these two values are 0. Therefore, EI into Y is equal to WL power 4 by 30. Therefore, Y is equal to WL power 4 by 30 into EI. This is the deflection at free end. Now, so deflection at fixed end. It means now calculate the deflection at fixed end. Fixed end, that is at x is equal to L. Simply substitute x is equal to L in this equation, that is equal to minus W into L power 5 by 120 into L plus WL cube by 24 into L plus WL power 4 by 30. So, EI into Y is equal to, so simply it is W L power 4 by 120 plus WL power 4 by 24 plus WL power 4 by 30. Finally, it becomes 0. So, this is the procedure to calculate the slope and deflection of a cantilever beam subjected to a linearly varying load. So here we have to remember only one point: calculation of intensity of load at section XX. This is only the new thing. Calculation of intensity of load at section XX. So for that we considered a part of the triangle as shown in this figure with the yellow color. So that is reproduced for our convenience. So here the height of the portion between the section XX and B is W suffix X. It is the base is X. As per the geometry, the area under this curve gives the total load. So we know that it is always concentrated centroid of a triangle BCD. Once you know the position of the load distributed linearly within the portion that is between X, section X and B, and the definitive perpendicular distance from the section XX to the WX square by 2L, you can find out the moment. That is the important parameter in calculation purpose. So then the rest of the thing is same. Afterwards, you may follow the same procedure, whatever the procedure we adopted for calculating the slope and deflection at any point. So tomorrow we will see the simply supported beam subjected to various types of the loads by using the double integration method for calculating the slope and deflection. Thank you.